Welcome back. Let's go to my bed and reading. It's Friday. It's 4 p.m. So let's read more. I'd like to read about these three jet engines. So then I need to cook some hot foods later. Not later, but like 1 hour I will start cook some hot foods. Oops. I'm trying to adjust my camcorder. So I will go to my bed and just read. Then I will cook some foods. Just need to boiling some rice.
General Electric GE9X. For the similarly named engine which powers the Boeing 787 and 747-8, see General Electric GE9X. The General Electric GE9X is a high-bypass turbofan developed by GE Aerospace exclusively for the Boeing 777X. It first ran on the ground in April 2016 and first flew on the 13th of March 2018. It powered the 777-9's maiden flight in early 2020. It received its Federal Aviation Administration (FAA) type certificate on the 25th of September 2020. Derived from the General Electric GE90 with a larger fan, advanced materials like ceramic matrix composites, CMCs, and higher bypass and compression ratios, it was designed to improve fuel efficiency by 10% compared to the GE90. It is rated at 110,000 lbf, 490 kN, of thrust, which is 5,000 lbf, 20 kN, less than the GE90 highest thrust variant, the GE90-115, rated at 115,000 lbf, 510 kN. Development, edit. In February 2012, GE announced studies on a more efficient derivative of the GE90, calling it the GE9X, to power both the -8 /9 variants of the new Boeing 777X. It was to feature the same 128 in, 325 cm, fan diameter as the GE90-115B with thrust decreased by 15,800 lbf, 70 kN, to a new rating of 99,500 lbf, 443 kN, per engine. The engine for the 777-8X was to be derated to 88,000 lbf, 390 kN. In 2013, the fan diameter was increased by 3.5 in, 9 cm, to 132 in, 335 cm. In 2014, thrust was increased slightly from 102,000 to 105,000 lbf. General Electric GE9X. For the similarly named engine which powers the Boeing 787 and 747-8, see General Electric GE9X. The General Electric GE9X is a high-bypass turbofan developed by GE Aerospace exclusively for the Boeing 777X. It first ran on the ground in April 2016 and first flew on the 13th of March 2018. It powered the 777-9's maiden flight in early 2020. It received its Federal Aviation Administration, FAA, type certificate on the 25th of September 2020. Derived from the General Electric GE90 with a larger fan, advanced materials like ceramic matrix composites, CMCs, and higher bypass and compression ratios, it was designed to improve fuel efficiency by 10% compared to the GE90. It is rated at 110,000 lbf, 490 kN, of thrust, which is 5,000 lbf, 20 kN, less than the GE90 highest thrust variant, the GE90-115, rated at 115,000 lbf, 510 kN. Development, edit. In February 2012, GE announced studies on a more efficient derivative of the GE90, calling it the GE9X, to power both the -8/9 variants of the new Boeing 777X. It was to feature the same 128 in, 325 cm, fan diameter as the GE90-115B, with thrust decreased by 15,800 lbf, 70 kN, to a new rating of 99,500 lbf, 443 kN, per engine. The engine for the 777-8X was to be derated to 88,000 lbf, 390 kN. In 2013, the fan diameter was increased by 3.5 in, 9 cm, to 132 in, 335 cm. In 2014, thrust was increased slightly from 102,000 to 105,000 lbf, 450 to 470 kN, and the fan diameter was increased by 1.5 in, 4 cm, to 133.5 in, 339 cm. In 2016, its list price was $41.4 m. The first engine was expected to be ground tested in 2016, with flight testing to begin in 2017 and certification happening in 2018. Because of the delays, the first flight test occurred in March 2018, with certification expected in late 2019. Ground testing, edit. The first engine to test, FET, completed its first run in April 2016. This engine completed 375 cycles in 335 hours runtime, which validated the engine design in terms of aerodynamic performance, mechanical system behavior and secondary air system heat management. The GE9X conducted icing tests in winter 2017. The FET was used for ground cold weather testing in natural icing conditions such as ground fog. Minor design changes using additive manufacturing were made within 1 month. Icing certification and evaluation finished during the 2017-2018 winter at Winnipeg, Manitoba. Simulated high-altitude conditions were used to test the GE9X for ice crystal icing, core icing, which was an issue for the GX. This testing improved the understanding of core icing as well as the more familiar rime ice. A design change required for the GX was the addition of bypass doors between the booster and high-pressure compressor, which open into the airflow path to reduce the chance of ice crystals entering the core. Design changes between FET and second engine to test, SET, addressed improvements required to meet efficiency goals. The minimum area in the duct between the HP turbine outlet and the LP turbine inlet was altered to set the operating line of the compressor, turbine and fan. The tip clearance at the front of the HP compressor was modified as a result of early running experience. Set testing started on the 16th of May, 2017, at Peebles, Ohio. 13 months after FET, it was the first engine built to the finalized production standard for certification. During the FAA 150 hours block test, the variable stator vane, VSV, lever arm failed and its redesign led to a 3-month delay. Set was followed by 4 more test engines by May 2018. The certification program began in May 2017. 8 additional engines were involved for certification, as well as one for a TOPS certification installed in the aircraft nacelle. A core engine was tested in the Evendale, Ohio, altitude test cell to check blade vibrations, and engines 003, 004, and 007 were assembled in 2017, and the 4th engine was used for flight testing later in the year from Victorville, California. In 2018, 10 compliance engines, including 2 spare engines, were needed for the 4 777-9 flight test aircraft. Type certification was planned for the 4th quarter of 2018. On the 10th of November, 2017, a GE9X engine reached a record thrust of 134,300 lbf, 597 kN, in Peebles, a new Guinness World Record, breaking the GE90-115B 127,900 lbf, 569 kN, record set in 2002. The block test engine ran at its operational limits, at triple red line conditions, maximum fan speed, maximum core speed, and maximum exhaust gas temperature. Icing tests started in Winnipeg at the end of 2017. The initial 777X flight test engines were shipped in 2018 for an initial 777-9 flight in early 2019. A quarter of the certification testing was done by May 2018. Icing, crosswind forward/inlet distortion, fan and booster blade vibrations, HP turbine blade vibrations, and thermal survey. Flight testing, edit. As it was larger than the GE90, the GE9X could only be installed under the wing on the Boeing 747-400 with its larger main gear struts and bigger tires, and not the previous 747-100 GE test. The engine was tilted 5 degrees more than the GE GF9X. Boeing built a specially designed pylon for the test. Suspended on a 19 feet, 580 centimeters, strut, the 4th engine of the program began flight testing at the end of 2017. The engine, with a fan diameter of 134 in, 340 centimeters, is installed in a 174 in, 440 centimeters, diameter nacelle, with 1.5 feet, 0.46 m, of ground clearance. The engine and nacelle weighed 40,000 pound, 18 t, with its new pylon and wing strengthening, compared to 17,000 pound, 7.7 t, for the CF680C2S and its pylon. In February 2018, the GE9X's first flight was delayed by problems discovered in the high-pressure compressor, HPC, variable stator vanes, VSV, lever arms. Also a routine check on the 747 test CF6 engines discovered fan case corrosion and high-pressure turbine airfoils on allowable limits. It first flew on the 13th of March with the previous design of the VSV lever arm. In early May, the first flight test phase of 2 was completed after 18 flights and 110 hours of run time. The GE9X high-altitude envelope was explored and its cruise performance evaluated. The second phase was scheduled to begin in the 3rd quarter. By October 2018, half of the certification was completed, and 8 development engines were used, mostly in Peebles, Ohio. #1 was stored. A fan blade was deliberately separated from the fan hub of #2 at takeoff thrust for the blade out test. #3 was used for crosswind ground testing and cyclic and load testing of the thrust reverser cascade assembly. #4 explored boundaries of the flight envelope such as low altitudes. #5 ran an endurance test with rotors deliberately unbalanced to make the engine shake at the vibration limits allowed in service, a requirement for a TOPS certification. #6 did ingestion tests later in 2018, after LP turbine over temperature tests. #7 did a second icing test phase in Winnipeg, Manitoba. #8 did the triple redline FAA 150H endurance test. 8 compliance engines, plus 2 spares, were required for 777-9 flight testing. A second phase, of 18 flights, began on the 10th of December to evaluate the engine control software and hot and high performance and lasted until the first quarter of 2019 before FAA certification the same year. By then water ingestion, crosswind, blade out, hailstone, bird ingestion and block or endurance testing had been completed. Flight tests were based in Victorville, California, and ranged as far as Seattle, Colorado Springs, Colorado, Fairbanks, Alaska, and Yuma, Arizona. By the 4th of January, 2019, 8 test flights and 55 hours of run time had been completed. At the end of January, the turbine case and rear frame strut were damaged during the blade out test and relevant components were redesigned. In early May, the flight test program was completed after 320 hours run time, during which high-altitude cruise fuel burn was established. Engines were modified to a final certifiable configuration standard before the maiden flight of the 777X, delayed beyond the previously expected the 26th of June by a stator problem at the front of the 11-stage high-pressure compressor. Before certification, final tests included a full durability block test, replacing the usual triple redline test at maximum EGT and both rotor speeds, as modern high bypass ratio engines cannot achieve all maximum conditions near sea level. The high-pressure compressor stator redesign delayed engine certification into autumn, which delayed the 777X first flight until January 2020. On the 25th of January 2020, the GE9X had its first flight on the 777X, flying for 3 hours and 52 minutes, before landing at Boeing Field. On the 28th of September, GE announced its FAA type certificate, as 8 test engines completed 8,000 cycles and 5,000 hours of running. ETOPS approval needed 3,000 ground test cycles to be completed as a requirement for entry into service. In 2022, a different issue with the GE9X paused testing of the 777X. Design, edit. The GE9X increases fuel efficiency by 10% over the GE90. Its 61:1 overall pressure ratio should help provide a 5% lower thrust-specific fuel consumption, TSFC, than the XWB-97 with maintenance costs comparable to the GE90-115B. The initial thrust of 105,000 lbf, 470 kN, will be followed by 102,000 and 93,000 lbf, 450 and 410 kN, derated variants. GE invested more than $2 billion for its development. Its nacelle is 184 in, 4,700 mm, wide. Most of the efficiency increase comes from the better propulsion efficiency of the higher bypass ratio fan. The bypass ratio is planned for 10:1. The fan is housed in 134 in 340 cm diameter case. The GE9X has 16 blades, whereas the similarly sized GE90 has 22 and the smaller GX has 18. Having fewer fan blades reduces the engine weight, improves aerodynamic efficiency, and allows the low-pressure LP fan and booster to spin faster to better match its speed with the LP turbine. The fan blades feature steel leading edges and fiberglass trailing edges to better absorb bird strikes with more flexibility than carbon fiber. Fourth generation carbon fiber composite materials, comprising the bulk of the fan blades, make them lighter, thinner, stronger, and more efficient. The GE9X also uses a carbon fiber composite fan case, first developed for the GX, to further reduce weight. The high-pressure, HP, compressor is up to 2% more efficient. As the 129.5 in, 329 cm, GE90 fan left little room to improve the bypass ratio, GE looked for additional efficiency by upping the overall pressure ratio from 40 to 60, focusing on boosting the high-pressure cores ratio from 19:1 to 27:1 by using 11 compressor stages instead of 9 or 10, and a third-generation, twin-annular pre-swirl, TAPS, combustor instead of the previous dual-annular combustor. Able to endure hotter temperatures, ceramic matrix composites, CMC, are used in 2 combustor liners, 2 nozzles, and the shroud up from the CFM International LEAP Stage 2 turbine shroud. CMCs are not used for the first stage turbine blades, which have to endure extreme heat and centrifugal forces. These are improvements planned for the next iteration of engine technology. The first stage HP turbine shroud, the first and second stage HP turbine nozzles and the inner and outer combustor linings are made from CMC, only static components, operating 500 degrees Fahrenheit, 260 degrees Celsius, hotter than nickel alloys with some cooling. CMCs have twice the strength at 1/3 the weight of metal and require 59% less cooling. In total, the engine has 65 CMC components, the most of any commercial aircraft engine at the time of its introduction. The compressor is designed with 3D aerodynamics and its first 5 stages are blisks, combined blade disc. The combustor is lean burning for greater efficiency and 30% NOx margin to seek forward/8. The compressor and high-pressure turbine are made from powdered metal. The low-pressure turbine airfoils made of titanium aluminide, tile, are stronger, lighter, and more durable than nickel-based parts. 3D printing is used to manufacture parts that would otherwise be impossible to make using traditional manufacturing processes. Specifications, edit. GE Aviation GE9X. Variant 105B10. Type dual rotor, axial flow, high bypass turbofan. Combustor single annular twin annulus premixing swirler. Control dual channel FADEC. Compressor 1 fan, 3-stage LP, 11-stage HP. Turbine 2-stage HP, 6-stage LP. Fan 134 in, 3,404 mm, diameter, 16 wide chord composite blades. Length 224.0 in, 5,690 mm, fan spinner to TRF aftmost flange. Width height 161.3 163.7 in, 4,097 4,158 mm. Bypass ratio 9.91. Overall pressure ratio 61, HPC pressure ratio 27:1. Weight 21,230 pound, 9,630 kilograms. Takeoff thrust 110,000 lbf, 489.3 kN. Max continuous thrust 103,500 lbf, 460.4 kN. Thrust forward / weight 5.2. RPM 100% LP 2355, HP 9561. See also, edit. Related development. 1 General Electric GE90. 2 General Electric GX. Comparable engines. 1 Rolls-Royce Trent XWB. 2 Rolls-Royce Advance, Future. Related lists. 1 List of aircraft engines. References.